Hello. In previous podcast we explained how we can use analytical solutions to solve the governing flow equation, and we apply these solutions for interpreting infiltration experiments and to estimate soil hydraulic properties. Analytical solutions are, however, limited in scope. They can only be applied to analyze simple flow conditions, such as flow into a homogeneous, isotropic soil subjected to simple initial conditions and simple boundary conditions, and subjected to simple soil hydraulic parameterizations. In practice, we will very often be confronted with situations that violate these conditions. Real soils are heterogeneous, and the initial and boundary conditions and the soil hydraulic functions cannot be reasonably be represented by simple mathematical functions. In these conditions, we should look for numerical techniques to solve the governing flow equations. Numerical techniques are much more versatile in scope. They can be applied to much more complex and realistic situations and play therefore a very important role in soil and water engineering. Yet the implementation of these numerical techniques is at the cost of loss of accuracy and increase in calculation time. In this podcast, we will explain how simple numerical techniques can be developed to solve the governing flow equations. Let's refresh our memory and recall the governing flow equation. To obtain our flow equation, we combine the Darcy flow equation with the mass conservation equation. Expressed in terms of volumetric soil water content, the flow equation is referred to as the Fokker-Planck equation, and it is expressed in the form of a nonlinear second-order differential equation. For practical applications, we need to integrate this equation. For integrating in time, we need defining the initial conditions. For integrating in space, we need to define the spatial boundary conditions. If all this is defined, as well as the soil hydraulic parameters d and k in this case, we can obtain explicit expressions of theta as a function of space and time. As previously explained, we can deploy analytical and numerical techniques to solve the nonlinear governing flow equation. Analytical solutions are mathematically very accurate, but only applicable when the flow conditions are very simple. Numerical solutions are mathematically less accurate, but they are much more versatile and applicable to analyze flow problems in complex heterogeneous soils, submitted to variable initial and boundary conditions. In this podcast, we focus on numerical solutions and illustrate the finite difference numerical technique. We illustrate the technique for solving the flow equation describing horizontal, transient infiltration in a homogeneous dry soil characterized by a constant soil-water diffusivity. For this flow problem, we developed in the previous podcast already an exact analytical solution. The numerical solution that we will obtain in this podcast can therefore be compared to what we have seen with the analytical solutions. Let's start with recalling our simplified governing flow equation, and let's recall the initial boundary conditions. We consider that the soil is initially dry, applicable at the value theta I, that the left-hand boundary condition is at x equals to 0 defined by full saturation, and that the right-hand boundary condition remains always dry. Most numerical techniques consider a discretization of the continuous space and time. Let's define such a numerical grid. Let's discretize the space, the continuous x space coordinate in this example, in a regular grid with g discrete spatial nodes. In this case, the spatial nodes are separated by a discrete space interval dx. Similarly, we can discretize the time domain in a set of n discrete time nodes separated by a discrete time interval dt. When developing numerical solutions, we are not aiming to obtain a solution of theta for all continuous space-time combinations, but only for the discrete nodes, which we refer to by discrete space and time indices, in this case G and N. Of course, if we consider a very dense grid, we approximate the continuous space-time domain rather well, and hence the numerical technique becomes more exact and precise. The densification of the grid will, however, be at a calculation cost. We need larger vectors, larger matrices to store and manipulate the discrete values theta, g, n. The question we should ask now is how can we obtain the discrete value of our state variable, theta, at a given grid point g and n? Well, if we know the value of theta in the neighborhood of the grid point En, then we can estimate the value at the location En based on knowledge of the neighborhood value, and we can extrapolate the value in the neighborhood towards the grid point we want to evaluate. If, for instance, theta varies continuously in space, we can estimate the value of theta at g plus 1, which means at the location separated from the location g, with delta x equal to 1, using what is called the Taylor series expansion. When ignoring the higher order terms, we can estimate the first order derivative with its spatial finite difference. In previous slide, we estimate the theta g plus 1 as a function of theta g. We refer to this as a forward solution. We can apply Taylor series expansions also in the other direction and obtain a backward solution, hence a prediction of theta g minus 1 as a function of theta evaluated at g. We obtain therefore a second possible approximation of the space derivative. The interesting aspect of numerical solutions is that different alternatives can be proposed to evaluate the differentials of our flow equation. Each solution will slightly modify the precision and accuracy of the solution. We will come back to this in another podcast. Here we show how we can combine previous solutions to obtain a third alternative for approximating the space derivative. We refer to this as the mixed solution. Graphically, we can represent the three previous solutions as follows. We have a continuous space theta x, and we aim evaluating the spatial derivative at a given point g. We therefore look for approaches that aims evaluating the slope of the continuous curve at point g, because that's what the spatial derivative is doing, calculating slopes of continuous functions. In this example, the first solution, the forward solution, will yield a slope that is slightly larger than the real slope at point g. The second solution, the backward solution, will yield a slope that is smaller than the real slope. The third solution will probably be the closest to the real slope. Hence, with the numerical discretizations, we were able to transform the first order derivative in a finite difference analog. We can now apply similar approaches for the second order term and apply different variants, as modulated, for instance, in this case, by the artificial parameter E, which allows to mix forward and backward solutions. For instance, if we consider E equals to 0, we evaluate the second order derivative in terms of actual theta values. It is the theta values evaluated at time n. If we consider E equals to 1, we evaluate the second order derivative in terms of future theta values, which is theta values evaluated at time n plus 1. And when we consider E equals to 0, we mix both previous solutions and obtain what is called a Crank-Nicolson scheme. Let's put the different pieces of the puzzle together to define a finite difference approximation for our horizontal flow equation. Using finite difference discretization in space and time, we can obtain the following expression. This is referred to as an explicit solution because we calculate theta at a given point in space g for a future time n plus 1 in terms of the actual theta values evaluated at different locations at G and in its neighborhood value. Alternatively, we can obtain an implicit solution, allowing to evaluate multiple future solutions in terms of a known solution theta and G. Still another solution is the mixed solution. Let's evaluate how the explicit solution works exactly. By reorganizing the equation, we obtain an expression of theta G evaluated at n plus 1. And this in terms of theta G in terms of n and its neighborhood values, G plus 1, G minus 1. Let's see how we can use this solution to solve the flow equation. Let's consider our numerical grid. We look to evaluate theta at each grid point Gn. The initial conditions and the spatial boundary conditions allow us to know the values at the limits of the considered space and time domain. Now we can implement an iterative loop and advance in time. For the first unknown node, we can calculate the n plus 1 with our updating equation, since all the theta n values are known. We update this for all space nodes and obtain as such the theta n plus 1 for all nodes. Knowing this, we can go a step further and repeat the same space loop. By iterating such a space loop within the time loop, we can obtain all values of theta for all points in the discrete space-time grid. For the implicit solution, we also rewrite our equation. If theta is known at a given moment n, we evaluate theta at n plus 1 at different locations simultaneously. Looking to this equation, we see that the solution becomes a little bit more complex, since we have now 3 unknowns and 1 known. The equation cannot directly be solved. Let's analyze how we can obtain a solution of this problem at the end of the space loop. We again have our numerical grid, and we again know our boundary conditions in space and in time. When starting the first space loop, we have a first equation allowing to write an expression with 2 unknowns. Since the left-hand boundary condition is known, we can now proceed in space and write the second equation, and we will have now a set of 2 equations but with 3 unknowns. And we can proceed this until we reach the end of the space loop. In that case, we arrive at the right-hand boundary condition. We will have n algebraic equations with n unknowns. Using linear algebraic techniques, we can solve this system of equations. Writing the equation in matrix form allows us to see that this problem simplifies into a matrix inversion problem. And solving the matrix inversion will allow to assess all future values of theta at time n plus 1 after having solved the space loop at time n. Subsequently, we can proceed to the following time step and solve the space loop again with the same technique. We can repeat this for all time steps and hence solve this for the complete space-time domain. Hence, our horizontal infiltration problem for a constant d can be solved. In previous slides, we showed how we can solve the horizontal infiltration problem with a constant d. In the case the d is not constant, as is the case in most practical application, the solutions becomes a bit more complicated, but the same principles as in previous slides hold. As such, we can formulate different finite difference schemes, like the first solution. This second solution, or a mixture of both. The difficulty here resides in the fact that we need to evaluate the nonlinear d in the solution. We need to evaluate a future d in terms of theta, but during a space and time step we do not know yet the future theta. So we have a kind of a chicken and egg problem. For obtaining theta at n plus 1, we need to determine d that depends on theta and that is also evaluated at n plus 1. In such cases, the solution is obtained by iteration. We We estimate theta at n plus 1 based on a heuristic rule. And subsequently, we evaluate day and solve the transport equation, which allows to obtain a second estimate of theta at n plus 1. If this second theta at n plus 1 is very close to the theta at n plus 1 obtained by the heuristic rule, then we consider that the estimate of theta with the heuristic rule is appropriate. If not, we try another heuristic value of theta n plus 1 and iterate until convergence is reached. Hence, for solving the horizontal flow equation, we can write the following equation and use A, B, C to simplify the writing. For instance, for a spatial grid composed of 4 unknown nodes, we can write the following set of equations. We have 4 equations with 6 unknowns. But thanks to the left hand and the right hand boundary condition, this reduces to 4 unknowns in total. We can therefore solve this set of equations easily by means of standard linear algebraic techniques. In the following notebook, some of these concepts will be further illustrated. The numerical solution will also be compared with the analytical solution. Please have a look to these following Python notebooks.